Okay, so we already went over some of lesson 1.3 in class, but since you're going to be doing the homework this week, I figured I'd just go ahead and run through it again a little bit. Complex numbers, remember, are numbers that have a real part and an imaginary part. So we talked about imaginary numbers, the solutions to the equation x squared equals -1. What are they? There are no real solutions to that equation because there's nothing you can square in the real numbers and get a negative number. So mathematicians came up with this idea of the number I, which is the number such that I squared is -1. And so that is called an imaginary number, and it's not imaginary because it's not real. I mean, it sounds like it's not a real number in the mathematical sense, but it is very useful for helping us work with numbers that we wouldn't otherwise be able to work with because they don't behave the way real numbers do. And so we use this idea of I squared equals -1 to kind of manipulate certain situations so that they will work along with the real numbers. So if b is a positive real number, then the square root of -b, we would not write that as square root of -b. We would write it as I times the square root of b. Because, just as I was saying, that imaginary numbers don't behave like real numbers. So for example, if you have the square root of -2 times the square root of -3, that does not equal the square root of 6. With real numbers, when you multiply a negative by a negative, you get a positive. But the imaginary numbers, you can't treat them like real numbers unless you rewrite them using I. So if we go ahead and rewrite this with I, and instead of leaving it as the square root of -2, we write I times the square root of 2. And instead of writing the square root of -3, we write I times the square root of 3. Then we can multiply those two things together. Square root of 2 times square root of 3 is the square root of 6. And then we have I squared. And since I is the square root of -1, I squared is -1. So that equals the square root of, it equals negative square root of 6. So using I lets us work with imaginary numbers, or these numbers that don't act right. And it lets us deal with situations we wouldn't be able to deal with otherwise. So if you have these kind of situations, you can never just start working with them. You have to always rewrite them in terms of I. So here we would write I square root of 9 times I square root of 25, and that would be 3I times 5I, which would be 15I squared. And I squared is -1, so that is -15. Similarly, over here, we could write I times the square root of 15 times I times the square root of 3, and that would give us I squared times the square root of 45. And since there's a factor of 9 in there, we can pull that out. And also I squared is -1, so we would have -3 square root of 5. And then here we can rewrite this as I times the square root of 50 over I times the square root of 2. And then we can go ahead and divide. The i's will cancel, and we will end up with square root of 25, which is just 5. So the imaginary number I is very useful. So a complex number has a real part and an imaginary part. So when we write a complex number, it will have a real part, we'll call that A, and it will have an imaginary part, we'll call that B times I. And so whenever we write them, you should always write the two parts completely separately. The real part first, the imaginary part second. Also, if you're dealing with a complex number like this, if a is 0, then you have what is called a purely imaginary number. If a is not 0 and if b is 0, then a plus bi is totally a real number. So what that tells us is that the real numbers are a subset of the complex numbers. Okay, so if you wanted to simplify these expressions, again, you have to deal with your I, and you want to write it in the form I just said. A, real part, plus bi, imaginary part. Two definitely separate parts. So for a here, 3 minus I times the square root of 100. So that's going to be 3 minus 10i. And you would want to write it like this. Real part first, imaginary part second, completely separate. Here, this looks like it's simplified, and it is simplified, but you want to write it, since it's a complex number, you want to write it with the real part first and the imaginary part second. This is the correct notation. Over here, again, you want to, first of all, simplify it. So you've got negative 6 plus I times the square root of 18 over 9. And the square root of 18 has a 9 in there, so you need to simplify that. So you'll have negative 6 plus 3 square root of 2i all over 9. So when you write the final answer, you're going to write the real part first. So that's going to be 2/3, negative 2/3, plus imaginary part second. That's going to be the square root of 2 over 3i. So you'll notice that even though those two fractions have the same denominator, I did not write them as one fraction. I wrote them completely separately because it's a complex number with a real part and an imaginary part. And this is how you need to write it. Okay, so you want to make sure you know the powers of I. I is the square root of negative 1. So when you square it, you get negative 1. That's what square root means. Then I cubed is just going to be negative 1 times I, so negative I. I to the fourth is going to be negative I times I, so negative I squared, so the opposite of negative 1, which is positive 1. And this cycle just keeps going on and on and on. I to the fifth is going to be I again. I to the sixth is going to be negative 1 again. I to the seventh, negative I to the eighth, 1, and so on. It just keeps going the same thing over and over again. So if you have I to the 48, that is going to be, you know that I to the fourth is 1. And since 48 is a multiple of 4, you know that this will be 1. It'll just be I to the fourth times I to the fourth times I to the fourth 12 times. And so therefore it's just 1 times 1 times 1 and so on 12 times. So I to the 23rd, 23 is prime, so it's not a multiple of anything. But we can still realize that how many I to the fourths there will be. We're going to think about I to the fourths because I to the fourth is 1, so it's an easy thing to deal with. So I to the 23 is going to be I to the fourth. How many times? Well, that would be I to the fourth to the fifth, okay, because that would be I to the 20th. And then there's going to be another factor of I cubed. So that is I to the 23rd. So I've got I to the fourth, 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 which is just 1. And then I'll have another I to the third. So I hope that made sense. I to the fourth to the fifth is I to the 20th, right? So I to the 20th. And then you've got I to the third. So that's I to the 23rd. So that means, since we figured out how many I to the fourths there are, this is all 1. 1 times I cubed is just I cubed. So I to the 50th, 4 doesn't go into 50, but we can say that it is I to the 4th to the 12th, which is I to the 48th, and then there's going to be an I squared also. So that's 48 plus 2 is 50. This is all 1. 1 times 1 times 1 times 1, and so on. And then we've got an I squared, which is negative 1. So I to the 50th is negative 1. I to the negative 19, well, when we have a negative exponent, that means we're going to go 1 over I to the positive 19. And so I to the 19, 4 goes into 19 4 times with 3 left over. So that's going to be 1 over I to the fourth times I cubed. So that is going to be, this is all 1, so that goes away, 1 over negative I, because I cubed is negative I. And we can't leave it like that because you can't have a radical in the denominator, remember. So we're going to rationalize it. We'll have to multiply the top and the bottom by negative I. Remember, I is a radical, so it can't be in the denominator. And that'll give us negative I over negative I times negative I is I squared, and that is negative 1. And so we just end up with I. Okay, so when we add or subtract complex numbers, we treat them just like any other polynomial. We add the like terms. So in this first one here, I'll just go ahead and write the real numbers first. Negative 2 plus 5 minus 3. And then I'll write the imaginary numbers. Minus 4i plus 2i. And then since I have to distribute that, that'll be plus 6i. And if I add negative 2 plus 5 plus negative 3, that is 0. That all cancels out. And I have negative 4i plus 2i plus 6i, which is just 4i. So if I wrote that in a plus bi form, I would write 0 plus 4i, but a plus bi. 0 plus 4i. 0 is a real number. Okay, so here it says subtract this from that. So we put 3/4 plus 9/5 I first. And then we're going to subtract 1/2 plus 2/3 I. So now we will get our real parts together. So 3/4 minus 1/2, and then 9/5 I minus 2/3 I. So 3/4 minus 1/2 is just 1/4. And then we have to get a common denominator of 15. So this would be 27/15 I minus 10/15 I. So when we add all that up, we're going to have 1/4 plus 17/15 I. So real part first, imaginary part second. So when we multiply complex numbers, we treat that just like we would treat any other polynomial, except that whenever we get an I squared in our answer, we have to remember that that is negative 1. So negative 1/2 I times 4 is going to be negative 2i, and the negative 1/2 I times 6i is going to be negative 3i squared. So this will be negative 2i plus 3, because I squared is negative 1, and negative 3 times negative 1 is positive 3. But we have to write the real part first and the imaginary part second. Here we're going to multiply out these binomials, and we'll just use the distributive property like we always do. So negative 2 times 4 is negative 8, and negative 2 times negative 3i is going to be positive 6i. 6i times 4 is going to be positive 24i, and then 6i times negative 3i is going to be negative 18i squared. So these are our real parts, because negative 18i squared is positive 18. So negative 8 plus 18, and then we have 30i. We're adding our like terms. 6i plus 24i is 30i. So that is going to be 10 plus 30i, and that is in the proper form. Real part first, imaginary part second. So complex conjugates. Remember, conjugates are two binomials that look exactly alike, except for the middle sign is opposite. So a plus bi, a minus bi, and normally when we multiply conjugates, we get a difference of squares. But when we multiply complex conjugates, we end up with a sum of squares because I squared is -1. So if you just look at this, when you multiply it out, you've got a squared minus abi plus abi. So those cancel just like they normally would with conjugates. And then bi times negative bi is negative b squared I squared. But since I squared is -1, we end up with a squared plus b squared. So when you multiply complex conjugates, you end up with a sum of squares. So here, this first thing is not conjugates. This is just squaring a binomial. And if you remember that when you square a binomial, you get a squared plus 2ab plus b squared. So it's the same way when you have 3 plus 4i and you're squaring that binomial. First thing squared, 9. 3 squared is 9, plus 2ab plus b squared. So you end up with 9 plus 6 times 4 is 24i, but this is going to be minus 16 because I squared is -1. So we will end up with -7 plus 24i. Real part first, imaginary part second. Now, multiplying complex conjugates, like I said, it's going to give you a sum of squares. So first thing squared, 5 squared is 25. It's going to be a positive 4 because 2i times -2i is -4i squared. I squared is -1, so -4 times -1 is positive 4. So we end up with 29. The imaginary part will cancel when you multiply conjugates. So the good thing about that is that when we want to rationalize a denominator, remember you cannot have radicals in the denominator of a fraction, and I is a radical. It is the square root of -1. So we'd have to multiply the top and the bottom of this fraction by the conjugate of the denominator so that we will not have any radicals. Oops, sorry about that. Plus 3 plus 5i. So when we multiply the top here, we're going to get 24 plus 40i plus 6i plus 10i squared. And then on the bottom, we're going to get a sum of squares. 3 minus 5i times 3 plus 5i is going to be 3 squared, which is 9, plus 5 squared, which is 25. So if we add up the real parts on top, 24 minus 10 is going to be 14. And then, oops, I forgot the I with the 40. It should be a 40i. When we add the I parts, we have 46. So plus 46i. And then the denominator is 34. And we have to write these completely separately. So 14 over 34 will be 7 over 17. And then 46 over 34 is going to be 23 over 17i. So it's completely separate. All right, 2 plus the square root of 3i to the -1 power is 1 over 2 plus the square root of 3i. And that's not okay because I have a radical in the denominator. I need to multiply the top and the bottom of that fraction by the complex conjugate of the denominator. 2 minus the square root of 3i. And when I do that, my numerator will be 2 minus the square root of 3i. And my denominator will be first thing squared, so 2 squared, plus the second thing squared. Square root of 3 times square root of 3 is 3. So I will write my final answer here in the proper notation with the real part first, so 2/7 minus the square root of 3 over 7i. Okay, on this last one, I just have an imaginary number in the denominator, so all I need to multiply the top and the bottom by to get that radical out of the denominator is just I. So I over I will give me -2i on top, and then 5i squared on the bottom will just be -5. So these become positive, so I just end up with 2/5 I. And if we wanted to write that in a plus bi form, we would write 0 plus 2/5 I.